Let's take a look at how encryption works. We can see here an example of hybrid encryption. In other words, we're going to use a combination of both symmetric and asymmetric encryption. This is commonly used if you encrypt an email with a product such as PGP or S/MIME. So let's take, for example, the sender of the message as an email message that they want to send to the receiver, but they certainly don't want anyone else to be able to read their message. They encrypt that message, the email message, with an AES key, using then a symmetric algorithm. This gives us, of course, the encrypted message. That encrypted message can be sent through an insecure channel to the receiver. But in order for the receiver to be able to read that message, they need that AES key. As we looked at before, we cannot send the AES key through the same channel as the actual encrypted email message. So what do? Instead, we take the AES key, the symmetric key, and we encrypt that using asymmetric key cryptography. So we take the AES key and encrypt it, say for example with RSA or elliptic curve cryptography, and we use the receiver's public key. That will give us an encrypted message, and in this case, that message is the encrypted AES key. We can send that through that same insecure channel, because even though someone is sitting in the middle of that channel, they will not be able to decrypt that message because they would need the receiver's private key. When the receiver receives the encrypted AES key, they can decrypt it using their private key, which will give them the AES key needed to decrypt the encrypted email message. So we can see that we've used the speed and confidentiality of symmetric key encryption, but we've supported that now through the use of asymmetric key encryption. This is an example used commonly and known then as a hybrid encryption model. We can also use encryption to prove integrity. Integrity is used to prove that a message has not been altered either accidentally through noise or some other disturbance on the line, or, of course, intentionally through an attacker then altering that message. It can also prove here that that message has not then been changed later by either party to the transaction. We don't want such that a person sends you a message and then later changes it and says, no, this was the original message. How do we prove message integrity? We've had a number of different ways over the years. One of the ways is through something known as a hashing algorithm. But we've had others such as parity bits and checksums, cyclic redundancy checks, and message authentication codes. These are some of the many ways that we've used to prove message integrity over the years. So let's see how a hash works. What we do is we take an entire message and we run it through a mathematical algorithm called, in this case, a hashing algorithm that then generates a computed or calculated value of that message. We could call that generated part a digest, or sometimes we'd just call it a hash. And that digest is an incredibly accurate representation of the message. If there was to be any change to the message, even a bit, that digest would change by a minimum of 40%. So if I have calculated the digest of a message before I send it, we can then validate that that message is the same by ensuring that it generates the same digest once that message has been then received. We can see that here graphically. The sender takes a message and runs it through a hashing algorithm which generates a digest. The digest is then appended or attached to the message, and the message is sent through this insecure channel to the receiver. When the receiver receives the message with the digest attached to it, they then take the message, run it through the same hashing algorithm to ensure that the digest they get of the received message is the same as the digest sent by the sender. This, of course, can be done using hashing algorithms such as MD5 and SHA-1, but there are some problems with this. If we put an intruder into the middle of that communications channel, they would be able then to alter the message and just to alter the digest and send the different digest along with the message. The receiver wouldn't realize that both the message and the digest have been changed. Either party could also change the message and claim, well, this is still the original. And there's no way to prove with this who the message came from or who it actually went to. Did it go to or come from the correct person? Or did it come from somebody masquerading or pretending to be somebody else? So here is a solution. We bring in the concept now of a digital signature. A digital signature is a combination of hashing and asymmetric key cryptography. The purpose of a digital signature will prove the integrity of the message as well as the source of the message. So we now have what we could call non-repudiation. The person who sent that message cannot later on claim that, no, I didn't send that message, or that's not the message I sent. So how do we do this? We go back to what we looked at just a moment ago. We create a digest of the message, but now we will actually encrypt that digest with a private key of the sender.